Hi, this is a brief overview of our work, Multimodality as Supervision. Self-supervised specialization to the test environment via multimodality. Most modern vision models follow the paradigm on the left. Pre-train on large-scale external data, often from the internet, and then deploy everywhere. But many real systems are not deployed everywhere. A household robot, an augmented reality device, or a domestic assistant may spend most of its life in one specific user space, or what we call the test space. So we ask, if the deployment space is known, can we build a model by learning from that space itself? To study this question, we formulate test space training, or TST, as a controlled sandbox. On the left is the generalist setup. A model is pre-trained on large external data, and then deployed across many different environments. In contrast, TST assumes that the deployment environment is known. We collect unlabeled data from that specific environment, pre-train a model on it, and then deploy it back in the same space. The important point is that this is still self-supervised. During pre-training, we do not use task labels from the test space. So this setup lets us ask, in a controlled way, how much a model can learn just from the environment where it will be used. This brings us to the key idea of the paper: where does the supervision come from? The answer is multimodality. In the test space, we can collect unlabeled data from multiple aligned sensors, for example RGB, depth, and other signals, all observing the same underlying physical world. Because these modalities are different views of the same scene, we can train a model to predict one modality from another. For example, given RGB, the model can predict depth, or vice versa. This is the core idea of cross-modal learning, and it gives us a self-supervised learning signal directly from the test space. Putting this together, test space training has 4 stages. First, we collect unlabeled multimodal data from the test space. This can include RGB images, depth, and other sensory or derived modalities. Second, we use this data for self-supervised pre-training. Third, to solve a downstream task, we transfer the pre-trained model using a small labeled dataset from external spaces. Importantly, these labels do not come from the test space. Finally, the transferred model is deployed and evaluated back in the same test space where it was pre-trained, on tasks such as semantic segmentation, object detection, and image captioning. For implementing cross-modal pre-training in TST, we use multimodal masked modeling as the self-supervised objective. We start with sensor-based modalities, such as RGB, depth, surface normals, and edges. These can be obtained directly from device sensors, or through simple transformations of the sensory data. We can also scale the modality set using off-the-shelf networks. For example, we use feature maps from models like CLIP and ImageBind, and outputs from task specialist models for detection, segmentation, and SAM edges, as additional modalities. This second setting should be interpreted as distilling existing models on data from the test space. So it is not a no external access setup, but it lets us ask whether specializing these signals to the deployment space is useful. On semantic segmentation, note how predictions from TST are a lot more stable across viewpoints, as compared to generalist models trained on millions of external images. We refer you to our paper and website for results on more tasks and datasets. Next, we present a consolidated picture of our quantitative results. All models on this spectrum are equivalent in terms of architecture. The lower bound here is no pre-training, so basically scratch, and on the right, the upper bound is fully supervised learning. The gap between them is the playing field for pre-training methods to fill. We highlight 2 key points here. First, our best method, which leverages multimodality, TST-MM, roughly covers half of the way on this spectrum. Despite being performant, there is still room for improvement by developing better pre-training methods. Next, if we compare TST-MM and 4M21, the key difference here is the source of pre-training data. They both distill from the same pseudolabels, however, distilling them on test space data is more performant than on a large-scale external dataset. Now, we present an analysis, studying the trade-off between scaling modalities and scaling dataset size. We start with a model, train for 5 spaces, and then scale across 2 axes. The number of spaces the pre-training data is sampled from, and the number of modalities. We find that scaling modalities, in the same 5 spaces, is more performant than unimodal scaling of dataset size and diversity with external spaces. Next, to the specialization-generalization trade-off. For this experiment, we start with a large set of spaces, which also includes our test space. We train on an increasing number of spaces, and evaluate it on two scenarios. The test space, which measures specialization, and a set of held-out spaces, which measures generalization. We find that this reveals a trade-off, whereas we increase the number of pre-training spaces, generalization as expected, improves, but specialization to the test space is hurt. Lastly, to support future work in this direction, we open source an iOS app, which collects multi-sensory data from a custom space, using any iOS device. It lets you collect aligned data from sensors such as RGB, LiDAR, IMU and ambient lighting. The key takeaway from our work is that test space training learns specialist models by cross-modal learning in the test space. Thank you for your attention.